Okay, hello everyone, I'm Giulio, and today I want to give a talk to you regarding just-in-time recompilation, WebAssembly, and scary noises, trying to bring it as a gentle introduction somehow. So at my main job, I work at this company called Flux, and we're building a PCB editor that works on the browser. So I work with web technologies that are supposed to run fast, but that's not the only thing I do. Other than developing web applications, I also really like low-level stuff, things like reverse engineering, coding in C++, looking at chips through a microscope to understand how they work. And today I wanted to do a talk that is a bit more focused on that. And especially some time ago at 13NC3, I did a talk called From Silicon to the Root Sandstorm, breaking famous synthesizer DSP, in which basically I presented how, together with another team of developers, we looked into all the, like from the 90s, digital synthesizer, and that was like very famous and used in a lot of famous music from the time. And since a lot of people were trying to reproduce it but failing, we asked ourselves, can we just emulate it the same way that we emulate an old gaming console? Because if this thing is just running software inside of it, that means that if we manage to extract the software, then we can just run it and we can basically preserve this for the future, so that the same way that you can still play Super Nintendo games with an emulator, you will be able to play the synthesizers as well. The problem though is that once we extracted the software from it, we noticed how basically it used a special chip called DSP for generating sound, which effectively does math. And if we wanted to emulate it, we need to execute the bytecode that this DSP executes. But unfortunately, the bytecode was completely undocumented, it was a completely custom chip, and all of the program looked like a bunch of random unknown bytes. How do you go when you have something like this, some bytes that for sure represent some instructions, but you don't know what kind of instructions those are? How do you execute them? Well, we started first with reverse engineering the custom processor by decapping the chip and by looking at all the wires inside the chip and how they interact between each other. We noticed how there were a bunch of areas that were RAM, a bunch of areas which was standard cell logic, and we started putting the pieces together. And standard cell logic, it's something like this. It's essentially a bunch of AND or XOR logic board flip-flops, latches, and a lot of normal digital electronics things, just put together in a layout and all connected between each other to form a very complicated circuit. That's essentially a way to convert some code like Verilog into silicon, and that's how they manufacture the chip. So ideally, we would have been able to just trace all of those wires and figure out precisely how the chip works. We partially did that, but also we did a lot of reverse engineering of the bytecode by glitching it and by just injecting programs and validating hypotheses. If this thing just runs programs, it means that we can send some programs, see the results, and start figuring out the bytecode that way. So that's how also with the combined approaches eventually gave us an emulator. If you want to know more about how we did it, the talk is at Congress. But the idea is that eventually we ended up with this UI, which is the emulator package as a plugin, which is like running the low-level code, and it's quite fast now, and it's usable for music production. The entire UI that you see was built with C++, HTML and CSS. Essentially, we have a bunch of C++ that takes HTML and renders it to OpenGL commands. And the problem, though, was that originally the performance of the emulator itself was really, really bad. The idea is that when you're running an emulator like this, you want it to run in real time. If you're running a gaming console emulator, you want it to run at least the gaming console at the original speed that it runs. Because if it's slower, then you would basically just see stuttering. And that's what we saw with this emulator, making it playable initially. Why is it so slow? Well, the idea is that if we just run a naive interpreter, what we need to do is that we need to get each command on the DSP bytecode, decode it, so like get from all of those bytes what are the different parts of the instruction using bitwise operations, then pass the type of the instruction into a gigantic switch case that, depending on which kind of instruction it just runs different handlers. One for load, one for store, one for multiply, one for jump, and so on. And that's the naive way to build an emulator, which works, but it's really slow. And the problem is this part here. If we have to, every time that we run a program, do a for loop on each instruction and decode them and dispatch them, that wastes so many instruction cycles that we could just skip. In fact, wouldn't it be nice if we were just able to convert each bytecode instruction into x86 or ARM bytecode and then concatenate them together and then execute them? And we pursued this idea for a while, and eventually we finished implementing it. And this was really, really fast. Like on my old MacBook, this basically was a speed up from 0.7x real time to 5.2x real time, which means that you can run on a single core 5 of those programs, and it will just run without a problem, which was really nice. And probably a lot of you people are asking, wait, is this something new that you invented? Absolutely not. This is just in time recompilation. And which it's the generic term that means taking some code or something that was meant to run on a certain architecture, convert it just in time at the last possible moment to the new architecture, and execute it during runtime. And in fact, this is not something new. Probably your favorite programming languages are already using this under the hood. Like if you think about Java, C#, JavaScript, recently also Python, they are all converting their code into ARM, x86, RISC-V, whatever, and then executing it. And in fact, the reason why JavaScript right now on the browser is so fast, it's because they invested so much effort, time, and money into making it JIT recompiled with very complicated algorithms. And suppose that, for example, for JavaScript, we wanted to build a naive interpreter, in fact. We will need to first parse the language, go through all the tokens and convert it into an abstract syntax tree. Then we need to go through all the tokens of the abstract syntax tree and dispatch all of those, so do the giant switch case. Then we have the problem that we have dynamic types. Each one of those variables that you see there, it's not really typed, it's typed dynamically, so the interpreter cannot make any assumption about what is being passed. And also, we have the problem that functions in JavaScript are complicated. They are closures. They need setup, and they need destruction, and there is the garbage collector. And all of this basically destroys the cache locality. Because if we're doing something like a tight for loop that just iterates through an array, if every time we have to jump over and over in different places of interpreter, this basically makes it incredibly slow. But if you think about it, you can see how that kind of code actually could, in theory, just be translated to 12 instructions in x86. Compared to something like that, that's probably it's a few millions of clock cycles. And of course, as I said, there are a few problems of doing that. But doing something like this is actually very common. And not only programming languages do that. There are a lot of emulators that do that. For example, Dolphin that converts in real time the code for the Wii or the GameCube into your current host platform. Or QEMU, which if you don't have virtualization, you can also do JIT. And for example, convert x86 into ARM so that, for example, I can run old Windows or Windows 11 on my MacBook. And one problem when doing this, though, it's how much do we want to JIT? Because JIT means just in time. JIT means that it's something that we're doing as the program executes. It's not realistic for example, a JavaScript interpreter to just take your entire program, your entire web page, and convert it to your local machine code and then execute it. Because it would be incredibly expensive at the startup. Like, you just open your web page and you just have to wait 10 seconds for everything to be compiled. That would be completely impossible to do. And also, we have the problem with dynamic types. We cannot convert this to assembly yet because we don't know what kind of things are going to be passed into that function. You will need to do static analysis, which it's not even possible sometimes in some languages. And also in JavaScript, you have the problem that you can do evals, you can import code, you can load code from another source. So you can't even know at load time how much code you have. And those are things that prevent doing full compilation of those kinds of languages. And this is not only a problem with JavaScript and Python and so on. This is also a problem if you're building an emulator. If you're building an emulator that, for example, that's a screenshot from the PS1 emulator, I think, you cannot know in your entire ROM, for example, what is going to be code and what's going to be data. And you can try to predict that, but then you will make mistakes for sure. And you can have self-modifying code, which basically makes this even more impossible because you will need to run the code in order to be able to get the code, and no, that's not feasible. And also, you will need to simulate interrupts and timers, which you can't really port to an x86 machine. So the solution here is that we can do JIT in blocks. We can take some JavaScript code and we can run it with an interpreter. And as we run it, we start making some assumption. For example, we see that this thing is a cold function, something that gets called only once. This thing is a hot function because it gets called over and over once this happens. And so the interpreter can be like, that function is being called a lot of times. Maybe I can make the program faster by promoting it to a JITted function. And what is going to be the type of that? Well, I can do some statistics and see that out of the 1,000 times that function has been called, that was always an array of integers. Perfect, so we can make that assumption and we can do the JIT. And that's essentially how modern JIT engines work. They run your code and then they check what are the most worthy part of the code to be JITted, and they do those first so that they are very efficient with code load and stuff like that. In fact, if you look at how V8, the engine of Chrome and Node work, it gets really complicated. You start with a naive interpreter, and when a function gets warm, like it gets called 10 or 100 times, there is a first optimizer, Sparkplug. Then, if it gets called even more, it passes through maglev, which starts making some assumptions regarding types. And once the function, for example, gets called over and over and over, like imagine, for example, a render loop for a graphics application, then it passes through turbofan, which is like the biggest optimizer that makes aggressive speculation, and that's the one that pretty much has the best performance. But what happens if those assumptions are broken? For example, if we always, the optimizer sees that that's always an array of integers, but eventually maybe one time out of 1 million calls, it's not an array of integers, it's a string. What is going to happen there? Because the machine code cannot work anymore if it's a string. There are a bunch of guards put in place for that, and when that starts happening, basically you get this big fallback. It's called de-optimization, and that means that the JIT code that has been generated is not valid anymore because one of the assumptions was broken. So it just falls back to the original interpreter. And that's a thing that, like, if you're developing complicated JavaScript application, you have to be careful about, because that's one of the things that basically kills your performance. You make some function which is like a bit too dynamic and takes too many types of parameters, and the JIT just cannot figure out what is happening there. And turns out this is an extremely complicated topic. There are entire guides on how to write JavaScript code so that this does not happen. There is a very nice guide there, and we're not going to talk about this because this is a very complicated topic. But what I ask myself is, if V8, it's an extremely complicated machine that has like millions of lines of C++ code, can we build some sort of toy version of a JIT recompiler in JavaScript? And you might ask, why should we bother? Because we can do some very cool stuff. We can run virtual machines or game consoles at very high speed in the browser, or we can run other languages. So, for example, we can run Python on the browser and having actually run fast. And also, we can even do sandboxing. We can create a web page that executes JavaScript, but the JavaScript that it executes cannot affect the JavaScript outside. It's a bit of an edge case that there are better ways of doing that, but that's another fun thing to try. But if you are in a browser, what should the JIT output? Because if we are like a native application, of course, we can emit ARM or x86 and we can execute it. But if we are on a browser, we cannot really execute a native program. But we can execute JavaScript and WebAssembly. And there is a very nice example of this. There is a website that it's like a JIT recompiler for, well, more like ahead of time for brainfuck, that takes brainfuck code as input and just outputs this mess of a JavaScript as an output, which is like a very optimized version of that brainfuck program that runs in JavaScript instead. Or there is this very cool website called V86, this library, which is basically an x86 PC compatible virtual machine that runs on your browser, and you can use this to load the ISO of Linux and just boot it inside your browser. And how it works is that essentially it's on the fly, does what QEMU does, and converts x86 into WebAssembly, and then it executes it. So it's many layers of JIT, but it's funny that this works, and it's actually surprisingly fast if you're running something like old versions of Windows. And the problem is that, though, that if we want to output WebAssembly, it's not that easy, because x86 and or normal assembly languages and WebAssembly are quite different. On x86, you essentially have a register machine, and the control flow is based on jumps. In WebAssembly, instead, you have a stack machine. You don't really have registers, so you need to simulate them somehow. And the control flow, it's not really jump-based. It's you cannot even do unconditional jumps. You can only do structured control flow, which makes it a bit more complicated if you want to convert a few things. And in fact, there was an entire paper written about this topic, which is mscripten. And the story is that originally someone just wanted to try to convert LLVM, so C++ programs, into JavaScript. And for this, they invented an algorithm that was able to convert like a LLVM control flow into JavaScript control flow. And then they developed a subset of JavaScript to make this as optimized as possible, called ASM.js. And then they figured out that they could have a binary representation for this, and they developed WebAssembly. So that's a bit the history. It just started from someone that wanted to run C code on the browser, and he ended up with like a standardized spec that went through a few abandoned specs like ASM.js. And another problem that we have is that WASM cannot JIT itself. And that's such a bummer, because on x86 you can, for example, just allocate some memory and jump into it. In WASM, it's not a von Neumann machine. It's a Harvard machine. Once you are in WASM, you cannot execute other WASM code. There is just a proposal right now to be able to do that, but pretty much no one supports it. So that's not an option, and that's a problem that we'll have to solve later. But I talked about WASM. Let's take a look at it, because I think it's quite interesting before understanding how it works, before we actually do a JIT for it. So we have two formats. One is WAT, WebAssembly text format, which is very similar to Lisp, actually. And it is that it's something between a normal assembly and programming languages. You see that you have, in fact, functions, you have parameters, you can define which type things are, and you can have calls, like for example, you can get two variables and then add them together, and you can do exports. And this normally gets translated into a binary format, because it's way more efficient to be executed. WAT stands for WebAssembly textual format, probably because WTF was not an option, was an acronym. And how many data types do we have? Well, 4. That's it. You have 32, 64-bit integer and float. Do you want a string? Well, that's an array of integers. Do you want a struct? Well, integers. Which, yeah, it's low level. And it's a stack machine. That means that if you want to add two numbers together, you need to push them to the stack, and then called add, which will pop two numbers and sum them together and put the result back into the stack. And it has linear memory. You can have like one very big byte array in which you can read and write with a pointer. And it's growable with 64 kilobyte pages. That means that essentially, like on WebAssembly 32, you can have like a giant array of memory, which is 4 gigabytes, bit less in practice. But if you're using WASM 64, you can technically allocate up to 16 gigabytes of RAM, which is really nice on a browser. And it's a stack machine, but actually it's not, because you also have local and global variables, which means that on your function you can also have an escape hatch for the stack and just set some variables that stay there. So it's a bit messy, but it kind of works. That's pretty much all the instructions that there are. You have normal numeric function, constant, comparison, addition, subtraction, and so on, conversions between 32, 64, floating point stuff bitwise. You have control flow, branch, function calls, loops, if else, and so on. You have memory, essentially load and store. And then you have, well, as I said before, local and global variables that you can get and set. And this is the entire overview of the WebAssembly instruction set, which, as you can see, it's quite limited. But if you think that this is an assembly language, this is Turing complete, and you can do pretty much everything with this. In WebAssembly, you have functions. You can, for example, define a function called get16, which has a return type of integer 32. And the return value of a function, it's just the last element that was pushed on the stack. So in fact, this just pushes 16 on the stack and then just returns it. You can also have parameters that you can get as local variables. So this is how you would implement an addition function in WebAssembly. You get one parameter, and it gets pushed into the stack, and then you do add, which adds them together, puts the result on the stack, and that's the return value. And as you can see, it's very low level, but there is not much to know about it. And a very important thing that you have, which is how you interact with the rest of the world, it's export import. In fact, you can import JavaScript stuff, and then you can export functions to JavaScript. All the stuff that you import, you have to inject it. So for example, you can inject a log and a math cosine function, and then you can just call it as if it was a WebAssembly function. And then you can also export functions so that then they become visible to the JavaScript part. And this is pretty much just an example of how to integrate the two languages. You load the WebAssembly binary, you can inject the imports that you want, and then you can just get out of it the functions that you can call. So this means that essentially JavaScript is always in control, and WebAssembly is just some kind of external library that you can import and call whenever you need. So now we know enough about WebAssembly. Let's create a WASM JIT for brainfuck. Brainfuck is a very fun language because it's incredibly simple. It's essentially a Turing machine. You have a very big data tape in which you can move the data pointer left and right, and you can increment and decrement the value at that point. And you have input and output, and then you have some very basic conditional loop thing, which essentially allows you to implement fully a Turing machine. And it's even worse than WebAssembly, honestly, to call stuff in, but it's Turing complete, which means that it's good as a toy language for building this kind of stuff. This is an example, for example, on how a hello world runs in WebAssembly. You have this tape in which you can move back and forth, and then you can increment and decrement it. And this way you can build the ASCII value for hello world and then print them. It's weird, but it's fun. And so the idea for building a JIT for this is that we can pretty much ignore the problem with blocks and just JIT into our program. And we can just build a for loop that goes through each WebAssembly instructions, which are 8 instructions, I think. And then we want to emit WebAssembly for each one of those things. Of course, now this basically means that we go through each one of the brainfuck characters, and then for each one of them we concatenate everything into a big program string, and then we should be able to just run it. So how do we map, for example, the brainfuck tape, in which you have this pointer that can move left and right? Well, we can model that with the WebAssembly memory. As we said, in WebAssembly, you have this concept of a big array that you can just write and read whatever you want. And we can use a local variable to keep track of the current data pointer. And then when we find the pointer left and right commands, we convert them into something that does like get the current pointer, sum 1, and then save it back. Or get the current pointer, subtract 1, and save it back. And those are essentially the 2 commands for moving it left and right. Instead, for doing something like incrementing and decrementing the value, unfortunately, we need to do modulo 256, because that's how brainfuck works. So we need to do some more stuff. We need to get the memory at that location. We need to add 1, and then perform a logic AND with 255. And that's how you implement an addition or a subtraction modulo 256. we then need to implement the input and output, those 3 commands there. And we essentially just do that with JavaScript imports, so that when we want to output something, we just send the result to JavaScript. And when we want to get something, we just get the input from JavaScript. The control flow, it's a bit more complicated, but essentially it maps really well to how WebAssembly works, because the brainfuck control flow, it's if the byte at the data pointer is 0, then go to the other closing character, otherwise go forward, which maps really well to basically a WebAssembly loop. The only thing is that we need to give a name to those blocks, so we essentially need to keep a stack or a running counter. And after all of this is basically how the JIT works. You have the input brainfuck code, and then we have a big switch case that, depending on which brainfuck command we have, it just emits the correct WebAssembly instruction, so that it does a for loop on all the brainfuck instructions and emit brainfuck WebAssembly code. And then essentially it just gets all of it. It converts it into compiled WebAssembly and just returns a function to execute it. And let's try it out. So can I just... Yes. So this is just just a simple web page that essentially runs the brainfuck JIT that I just showed before. And this is a brainfuck program that will give us some result. Let's try to run it. This is now running the WebAssembly interpreter and the JIT at the same time. So the interpreter will take a longer time, but the JIT will be a lot faster. In the meantime, you can see how the page froze because the interpreter is very slow. And now we wait. Why? Because that way we can compare how much faster the JIT is. Another important thing is that normally brainfuck is very optimizable. Like, you can do a lot of pre-processing. But here we're not doing any. Here we're just running the JIT version and the non-interpreted version to see the comparison. So, Mandelbrot. So the interpreter took 29 seconds. The JIT took 5 seconds. That's like 5 times faster. Which, even just by doing no optimization, just by doing JIT on that brainfuck code, that's orders of magnitude faster. And this is my new MacBook. On the previous one was much worse. Like it didn't even finish sometimes. So let's go back to this. Why did I talk about my talk at Congress at the beginning? Because I wanted to do something similar. That's the entire reason why I prepared this talk. Because I wanted to try, is it possible to take the emulator that we built back then and just run it on the browser? So how does the emulator works? Well, we have the UI, which is running in HTML and CSS, which, perfect, that's already HTML and CSS. We have the microcontroller emulator, which is like the main microcontroller of the synth, which controls the front buttons, the LCD, and the keyboard and stuff like that. And this microcontroller writes to 4 custom DSPs, which can be either interpreted or JITted. So if we want to run this, the emulator UI is already done. The microcontroller emulator, we can compile that to WASM. It's not JITted even the original emulator, so that's not going to be that big of a problem. It should just work if we just compile it with mscripton. And the difficult part is going to be this, because we need to convert the JIT that we did for ARM and x86 into WebAssembly. So first, to prove that it actually works, I just converted it this one interpreter, in which the entire emulator became a block of WebAssembly, a C++ class actually, in which it runs the CPU interpreter and the DSP interpreter, and it uses Canvas API to just throw the pixels from the LCD, and it uses the Web Audio API to constantly ask for new audio that is generated and to play it back. And we can see how well that is working now. I have it here. Probably need to enable internet though. Should have internet now. Okay. And this is the emulator without JIT. So it boots, it runs, and then we can try to play a node. That's not great. Why is it sounding so bad? Because it's less in real time. It's struggling to keep up, and the interpreter is just slower than what the audio output should be, so it just cannot produce audio in time to make this run. And now this probably also killed my Firefox. Okay, and so how do we solve this? As we said, we cannot do everything in a single WebAssembly block because WASM cannot JIT itself. We can have the WASM block generate its own WASM code for the JIT, but then it cannot execute it. It cannot execute it because there is no way to do that because of security reasons. So what is the hack that this thing does? Now we have the C++ emulator, which emits JIT for the DSP using binarium. And it essentially generates WASM binary code, which then gets passed to JavaScript, which compiles and caches. And JavaScript then just runs that as another WASM block that the Web Audio API will then call in a loop to generate audio. And this was basically possible because binarium, it's a very nice library that basically everything is built upon, which allows you to programmatically create WASM binaries in C++. For the original emulator, we used ASM-JIT, which is a similar library that does the same, but for ARM and x86. This is similar, as in you can, with a bunch of function call, generate WASM abstract syntax tree and then just compile them into a WASM binary. And now we can try how well that worked. So let's enable the JIT audio path. Let's start it. And then if we play a node, that's a lot better. And we can also play demo songs from the synthesizer. Now finally it works. And that's the emulator running at full speed on Firefox, which is a bit of a gamble because I never tried it before on Firefox. But yeah, it works. Nice. And so let's finish the presentation. Yeah, thanks. That's it. I had no more slides, surprisingly.